I will talk a bit about our experiments to do high-resolution imaging on this Cray machine, which is located in Finland, in Espoo, and it's operated by the Center of Scientific Computing. And here are some web pages if you want to check out the machine.
I will do my business.
And I have very few results on this thing, so I'll try to summarize them in the end. And first I try to give the motivation what we are trying to do and why we need high resolution simulations. And then I will talk a bit about the machine itself and how the TensorFlow performs in this particular machine. So what we try to do here is small-scale dynamo action, and this is the simplest possible problem you can. Well, you could do it without magnetic fields, but then it wouldn't be a dynamo. So we just consider isotropic MHD turbulence with a large-scale forcing, and this is isothermal. The Mach number is of the order of 0.1, and now there's these two numbers that you need to keep in mind. One of them is the Prandtl number, which is just the ratio of diffusivities, and then the critical magnetic Reynolds number, above which dynamo action happens, or above which the small-scale magnetic field grows. So the keeper of the bridge of death now asks the question. And this is really the only question you can ask about this system at the moment. So what is the dynamo threshold in terms of the Reynolds number for a given Prandtl number?
What is it?
I don't want to do that. The first, well, he always asks questions where first word is what. So what is your name, and so what's your favorite color? Not in this case. But then you can pick one of the pick an answer from this category of famous last words. That's easy. It seemed that it's easy. That's the critical Reynolds number increases according to more or less the Prandtl number to power minus 1/2. This was the situation basically 2 years ago, or maybe even last year. 4 years ago.
That was in the 2004 paper.
Okay, so 3 years ago. And well, this graph suggests that if we go to very low Prandtl number, for example, the sun Prandtl number is something like 10 to minus 6, it would seem that small-scale dynamo action is not possible, or it's very hard to excite. You have to have a really high Reynolds number. But this appears not to be the case because since then there has been some new computations with higher resolution and lower Prandtl numbers. So this is the part that you saw in the last graph. So it seemed that the critical Reynolds number increases indefinitely until this point somewhere here, Prandtl number 0.1 or so. The dotted lines here are Prandtl numbers 0.1, 0.01. But then it seems that it's, the critical Reynolds number seems to decrease after that. And this was quite surprising. And what could then be the reason for this? And for that we need to look at something totally different. The bottleneck effect, which is basically if you plot the energy spectrum of these high-resolution turbulent simulations, and then this is multiplied by K2 5/3, which is the Golden-Goro spectrum, and then it should be flat here, like inertial range. There you can learn some Finnish. This was the plot made by Axel for CSC news item. So inertiaalialue, this is inertial range in Finnish, and then the bottleneck effect is here, pullonkalla effect. And what it is that this bottleneck effect is that you see this bump here on the spectrum, and it's basically tells you that the turbulence has difficulty getting rid of its energy near the dissipation range. And if you then consider the case that you have a high Prandtl number, which means that the velocity fluctuations are damped at much larger scales than the magnetic field fluctuations, then you get a situation that the small scale magnetic field is on the range where the velocity field is smooth, so fluctuations are damped out. And it seems that in that case it's easy to excite magnetic fields, or the dynamo works easily. And then if you consider the other extreme, that you have a very small Prandtl number, then the small scale magnetic field is somewhere in the inertial range of the velocity field, where the velocity field is rough, which means that when you go to smaller and smaller scales, then the velocity gradients become bigger and bigger. And then it's more difficult to excite the dynamo, or it's thought that it may even be impossible to excite the dynamo. And but now it seems that the dynamo is still possible, but it's harder to excite than at high Prandtl number. If we look at this figure again, then basically this bump here occurs at around Prandtl number 0.1, which conveniently, also in this figure, I don't know if it's a coincidence, there's also a 0.1 here. And basically it occurs on the bottleneck effect itself, where the velocity field is at its roughest. And now if we go to low and lower Prandtl numbers, it may be that it's significantly or somewhat easier to excite the dynamo again.
Okay. Can you say again what you mean by rough? I mean, if you were to not scale this plot with k to the 5 then there wouldn't be a bump at the bottleneck effect. So why is it the deviation from the Kolmogorov scaling that makes the velocity field particularly poisonous for the dynamo? You know do that?
Well, you do it. You just copy.
First of all, the velocity difference is a critical thing that goes singular. So they go like the spatial separation to some power, alpha. Or in fluid dynamics, of course, we call it zeta. Right? And rough now means that zeta is less than 1. So as you make the separation is smaller and smaller, the gradient will go up like delta x to the negative power minus.
Basically, you cannot expand u in a Taylor series.
Yes, towards small scales.
What does it come along?
And unless zeta is 1, but that's exactly what happens, of course, physically at the dissipation range. Now, this is then related to a power spectrum, E of k, where k goes to the power minus 1 plus 2 times zeta. Getting what? So I'm going to get the corrections. So now if the, so that means if we say this goes to the power n, minus n, then theta of course translates to n minus 1 divided by 2. So if you now have an example of Kolmogorov, n is equal to 5/3. So that means we have 2/3, 1/3, that means, as we know. That's rough. if we have -1, if we have in the bottleneck, then this result becomes 0. That's very rough. Rough at least.
So what does it mean? It means that the velocity increment does not depend on the distance between 2 points.
No, it blows up. The gradients blow up. They become singular. With the smaller delta x, you go closer and closer together,
Yeah.
the gradients blow up.
Kind of
because
like-
the velocity difference is the same, but the scale over which it's different. It's the same. It's the smaller. That's why it blows up.
Yeah.
Okay.
That was what was last.
Okay.
And you sure about this exponent on 1 on the bottleneck? That's what you found here in your simulation?
It's too small a range to fit an exponent.
It's you can the bottleneck can be represented by a field of two exponents. One is -1, the other one is 5/3, and that has been done since the paper of Jackson, right? Yeah. And since the early 90s already, 93. It's a fit, really. It's not theory for that.
Okay, so what we would like to do is to get rid of the bottleneck effect, or do simulations in a range where the maximum magnetic field growth occurs away from the bottleneck effect, which means that we have to go to even lower quantum numbers. And this is where the problems really start numerically, because if you look at, for example, this last point here, something like quantum number 0.05, you need to have a magnetic Reynolds number of something like 200, and quantum number of 0.05 means that you have to have a 20 times higher Reynolds number for the fluid motions, which is 4,000. And if you consider how large a crit you would need to have for this, if you have a crit Reynolds number of 1, you would have to have something like 4,000 cubed. And well, this is a rough estimate, of course, but still you need to have as high resolution as possible in order to achieve this kind of numbers. And what is actually usually done is that if you look at the right curve, this is the usual Laplacian viscosity scheme, and usually people have used higher order hyperviscous schemes in order to get to these in this regime. And if you look at the,
In the Alexander paper, what was the resolution?
I think this was 512 cubed.
Spectral.
Yeah. And but if you then take another look at
Plus
this,
plus hyper actually, I think, right? You used hyper diffusion.
I think they have two different codes that they were using. One was spectral, and then the other one was finite difference. Oh, I'm not sure.
Is it Chicotica or?
Okay, if you take another look at spectra, is that you see that this is a direct simulation by Kaneda et al. On the Earth simulation with 4,000 cubed. And then if you look at these hyperviscous runs, then you see that the bottleneck effect is really saturated a lot. So it may also have an effect on the properties of the dynamo then. If the bottleneck is really too large, then maybe also the critical Reynolds numbers need to be higher. So ideally, one would like to do this with direct simulations, but I'll leave it at that at the moment and talk about something else, the computer, for example. So it has a really strange number of computing nodes. It's really 1012, not 1024, which would be much more logical. And each contains one dual-core AV processor. So it's about 2,000 cores in total. And each core has 1 gigabyte of memory available, which turns out to be another bottleneck effect for us. It appears. And the machine will be updated, so in the end of 2009 it should have another extremely silly number, 2024 processors with 4 cores each. And at least at the moment, the minimum and maximum job sizes are 64 and 512.
Is it normally what community normally uses this computer?
Well, it's there's actually it can be used by all universities in Finland. So it's there's different kind of projects going on there. So, but I think we are the only ones doing any fluid dynamics on this computer.
Does that mean there's also chemists running there?
Yeah, plenty.
How many total computers, physical computers, represents those numbers, 1012?
1.
Oh, okay.
And at the top 700, 500, where is it?
Sorry?
This machine, the top, the world powerful machine.
All the top 500.
Yeah.
They are on the list, but I don't know their exact. They actually have 2 different machines with 2,000 processors. So I'm not sure about the position. It's on their webpage, of course, because they dropped out of the list at some point and they made a big fuss when they got back on it. So. Okay, so then pencil code in this machine. So here I did a few tests. I started out with 64 cubed with 1 core, and then kept the problem size per core constant and went all the way up to 512, which was the largest one available. And the scaling is very good actually. Although here we do get some performance hit already because we don't have exponentiation. So there's
109.
only 16 trig points in one of the Y or Z directions, so this is already quite low. Although still it scales pretty well.
Is this in the manual?
That was my talk at least. And it may be already in the
Yeah, I saw
It would be good.
something, at least the data I saw in
But I had was
It looked really nice. So.
On which sample did you check that?
this was helical MHD turbo.
which by the way has the scaler turned on.
Not this one,
Not this one,
not
sorry.
helical.
Just to notify the data.
No, I mean we just have it in the particular sample, but the sample was also often used as a timing, but then only if it's not turned on. As you have to be turned on.
Yeah. Okay, so then the results, which are few. So we have only, well, a few 512 cubed runs, and well, all of them are decaying, so we don't have any dynamo of this resolution yet. And we would really need to do, because in this set we have one calculation with Prandtl number of 0.05, where we get Reynolds number of, fluid Reynolds number of the order of 1000, but then the magnetic Reynolds number is only 50, and this is definitely too low for dynamo to work. So we would need to go at least to 1000 cubed, but then we get to this, what I call the other bottleneck effect, which is the memory, which runs out. And if you do the math from here, then you can come up with a figure that's the problem size per 1 core. In this case, when you have 1000 cubed and 512 cores, is equivalent to 128 cubed on 1 processor. So I had a tough time, or I still don't know how to actually determine how much memory one run requires. If I run the code with the same setup, with 128 cubed, with 1 processor, and I go to the top, I see 2 figures, and I don't know which one to pick, or should I pick any of them? So
They shouldn't differ too much, I think.
well, there's a factor of 3 at least, or 4.
In that case, they can lower.
Okay, then it should be something like 300 megabytes.
But the problem is, of course, that the peak memory might be different. Well, I think currently for large ones, it's often start.x that takes considerably more memory than running the code.
Yeah, this is actually, we do a remesh. So
Okay,
we don't run
okay,
any.
yeah.
But how can start.x take more when it doesn't have the geo?
It has X, Y, and Z as a global array.
But that's just free.
Has a temporary variable. Okay, you're probably right.
Because
If
GFs
you
should
should
have
have a significant number of variables, but I think I found that if memory is tight and I can somehow get start.x to run, maybe I'm mistaken. I thought that then also run works, but maybe I did the test with.
But I think it's probably not X, X, and Y, Y. It's more all these TMP things that are defined in different places.
So does anybody else have this experience? I mean, it's not unusual. I had it many times for unexplained reasons. So that once you come close to the machine capacity, all of a sudden, even though the machine should certainly have, I mean, if it has 1 gigabyte, you should be able to use it 400 megabytes, you would think.
Yeah, they say on the manual
Even
pages
here,
that
300 is not enough.
you should be able to use 860 or something like
Yeah,
that.
and that doesn't work. I mean, we had the same problem already on the Origins machine in Trondheim, and then Niels Haugen reported this to the Crayfever, and then I think the situation then was that the machine itself uses for MPI to work a lot of space, and so the problem really came through the usage of MPI.
Well, this was after MPI. They specified how much memory you have if you have an MPI job, and this was this 860 or something.
But I mean, we can blame everyone else, but the thing is, the pencil code has not been optimized for. I mean, the core routines are optimized for memory, but not all the initial conditions for memory stuff. I think we're using way more memory than
He hasn't used it at the start.
But even in run, I bet you can find TMP files.
Yeah, but there's no global arrays that we don't need.
No,
Other than F and BF, there's no global arrays in run.
But the TMP file are they overwritten when you use that routine?
TMP file?
If you go into a routine like a Fourier transform thing, it has some TMP file of size mx and y and z. What happens with
with Fourier, well, if you once you leave the routine, the memory is freed again.
But
but without Fourier, there should not
be
be any global arrays other than F
turn
and
on
BF.
or off Fourier transform?
On.
Fourier transform takes some room.
But yeah, I did some tests then. There's a test queue where you can test all sorts of things. So I did a small run with, I believe, 128 squared times 256 with 2 cores without any power spectra, and it fails as well.
Mm-hmm. So that's then
So this is a comparable problem.
128 cube 1 also fails. Does that work?
Well, the problem, if you're running at one core, then you get the 2 gigabytes memory, so then that works.
So 128 times 256 is actually the exact same number of grid points on each processor. That is
exactly, yes. So that is kind of a strange problem. And then we did ask the guys at the CSC to how could we check how much memory our run is consuming. And then the answer came 3 days later saying that, well, you can't. It's quite complicated. You have to run some Cray's own debugging software or whatever in order to see this, and I haven't done this yet.
But I think this is a problem that other codes face also when they go to really high resolution. I know there was this SPH code that had something like 10 billion SPH particles with the gadget, and they had to make a slim version of their code. They had to slim down their code because of this memory problem. So they were really working first on cutting down everything out of the code that they didn't need, because everything takes up memory.
That's why we, of course, have a lot of these new modules.
But maybe we should make a lean version of principal code.
What do you want to strip out in order to save memory?
I can't say, but I bet if you go and look at it, if you look at how much memory the principal code takes, and we take how much is actually coming from DF and F, I bet there's a big overhead on that.
That's not true.
Right.
It's a
But
bet.
that's exactly what you check too, right? You can work it out, you can calculate, and it matches very closely.
Does it?
Some
You can do a
compilers,
top command on a laptop.
some compilers have problems with that. With Intel 8.1, we once investigated that, and we never really figured out. All the indications we have are that really the compiler does something strange and tries to allocate memory.
Yeah, right. So just having a new compiler all of a sudden on the same machine, you were able to run it again. Was this an old compiler 6.1?
Yeah,
That
I
was
think,
right.
I think the older version.
6.1 was working perfectly, right? 8.1 not at all.
Exactly.
I mean, only unless you had a 31 cube.
And with Intel compiler, I discovered last time that with the my spectral code that the size of the executable increase with the version. If you compile something with a 7.1, you take 200 megabytes, something like that. You compile with the last version, it takes 300 megabytes, and you don't know why. The size of the executable increase with the with the version of the compiler.
Yeah,
And
but
if you
that-
compile with it's because it's a F77 code, and if I compile with J-Fortran, the size of the executable is much more or less than the size using iFort.
But I mean that may also depend on optimization flags and stuff. Sometimes some data are put into the executable that you don't need to have there, but then startup is fast or something like that. I think so. This doesn't have to be. It can be well be, but it doesn't have to be related to the amount of memory the code really takes. But you can do top on that machine with our remote background top thing, or is top not running on the node?
Apparently not, or
Okay.
But you use a Cray compiler. In your case, which compiler do you use?
I think it's, well, I'm not totally sure. It might be the Portland crew compiler that they are using.
Cray has not its own compiler?
I'm not sure.
Well,
Ah.
the hardware is not Cray specific, so
Have you tried other compilers?
No, I haven't. Well, part of the problem is that only the front end is running Linux. The computation nodes are running something totally different, called Catamount or whatever. And apparently, the stuff that you compile to run your code won't run on the front end. It won't run on Linux. So it's a totally different system. So yeah, that might be an issue if you want to install your own compiler. Then it may be difficult. It may be impossible. But yeah, the workaround, of course, would be to be able to use 1,000 calls, which we requested, and request was denied. And well, maybe it's possible later on because they say that they would have another application round for big computational projects. So we definitely are going to try this one. And then, paradoxically, this is the machine to run big simulations. But they have another machine which has also 2,000 processors, and there you can use maximally 256 cores, but there you can get 4 gigabytes of memory per core. So if you decrease the number of cores by 2 and then increase the memory by 4, then you still get a gain of 2. So it should be possible to run this 1,000 cubed on this other machine, which is intended for smaller jobs. So I guess this is the someplace else we have to try first. And maybe I just quit there.